All right. The previous video, we kind of showed a circuit. If you recall, we looked at this circuit like this. I better go hit the pause button real quick. Apologize. Maybe I'll zoom in really quick on this. If you recall, we had this circuit and we had this function generator, and we would see that depending on what frequency you applied, we might see the lights light up. And we could see that as we change the frequency, there's one special frequency that seems to give the brightest light. Our goal is to go from this conceptual understanding of capacitors and inductors impeding current flow to a mathematical representation. To that end, let's look on this board here. Okay, so ignore these arrows for a minute. We're going to have a series LCR circuit, and we've got a source, an AC source. We've got the inductance, capacitance, and resistance. Now, I want to make clear what I'm talking about with these symbols. I really need to stress something here. This is not the source voltage. V0 is not the source voltage. It's the source voltage amplitude. If you recall, the voltage as a function of time was oscillating, right? And it was V0 times sine omega t. Okay? So to be clear, I'm talking about the source voltage amplitude is V0. The source voltage is this sine wave, and we'll get into that in a minute. In addition, you could measure the amplitude of the voltage across the inductor. Right? So, and to be clear here, I'm trying to color code this. Apologies if it doesn't work. There's the capacitor, has its own voltage amplitude, and the resistor has its own voltage amplitude. And now things are going to be a little bit tricky, right? We used to say, oh, well, the voltage, if we just take the source voltage and divide by resistance, we can get current. But now we have all three of these in here, and they did weird things. In particular, let me just jump to a simulation really quick. This is so complicated. If I try to say it in words, it might not make sense. So here's a case where I think the simulation, oh, and we don't want that. That looks funny. Here, this one. All right, and let me see if I can make this a little bigger. All right, let me see if I can annotate. Okay, and right now there's so much going on, it seems out of control. But first, let's look at some basics. We have an AC source, there's resistance, capacitance, and inductance. So this looks a lot like our circuit. It's an LCR circuit. Ignore everything except for what's in the circles right now. The issue that we have and that we discovered, let me clear some of these drawings. So actually, let me do this really quick. Right, we're wanting to look at these things right here. Okay, and those purple boxes don't show up that well. Let's make it bigger. There we go. So I'm looking at this information in here. We're looking at the source, and we're looking at all these sine waves. And maybe I'll put a box around this too. This is the current flow. All right. Now, if you recall, in the last video, we talked about how when you put capacitance in the circuit, the current would tend to lead the voltage. And when you put inductance in the circuit, the opposite was true. And what I'm saying here is, let me get I'm saying Eli, the Iceman, was a phrase we used before. And maybe actually, let me write that one in blue so it's color coordinated. The idea was we saw that current and voltage did not peak at exactly the same time when you used capacitance or inductance. In particular, since I have the blue marker out, we saw that current would peak before the voltage when you had capacitance dominating the circuit. And the opposite was true. We saw that voltage would peak before current when you had inductance dominating the circuit. Now, I want to bring your attention to these arrows. Look at these arrows carefully, and you'll see that the tip of each arrow is tracing out the voltage curve in 2D space. We call these arrows phasors. Now, the math is involved, and I don't want to do all of the math right now, but all I want to point out is you could see that this Eli and ice factor of leading and lagging is showing up. At any one point in the circuit, the voltages are not peaking at the same time. The voltage across the resistor is not peaking at the same time as the capacitor or the inductor. Now, because I'm not able to pause this video right here, well, I guess I could do what I'm going to do is I've got one on the board. So let's go to it here. So these arrows are supposed to represent the same thing. The idea is the voltage across the source, the tip of this arrow is supposed to be representing that. All right, so let's see if I can get this done. What's happening is, as the source is changing, right, its voltage goes up. This is like a positive voltage. And then, whoops, if I could keep rotating this around in a circle here. Let me get all these magnets close to the center. I think it'll make it easier. Sorry about that. Right? The idea is, as I rotate these, now there's no voltage from the source. Now the voltage from the source is negative. All right. And then we're finally all the way back around. The voltage is back to 0. Now watch the resistor. Think about, what does this resistor mean? Okay. Well, in this case, the voltage across the resistor is a drop. So that's why it's, the opposite sign of the voltage of the source. If we were going around this loop doing KVL, we'd say, oh, well, if I have a positive change in voltage here, I'd expect a negative change in voltage across the resistor. That's why the arrow is pointing the opposite way. When you get a positive voltage for the source, you get a negative voltage across the resistor, so to speak. Now here what we see is the capacitor. Now, if I recall correctly, what did we say? We said ice, right? So we know Eli the Iceman. I'm just going to write that up here. Eli the Iceman. All right. So in this case, look what's happening. We know that current, in some sense, has something to do with resistance. I'll go into this more, but you could see that in this case, we see the capacitance, its voltage is peaking after the current. How about I show you like this, right? Here's the voltage across the resistor, right? And we see that as this thing is rotating around, the capacitor peaks after that. Now, if I keep going around, the voltage is, the source voltage is peaking now. Okay. The voltage across the inductor is peaking, and then the resistance peaks, right? And so at this point, what we see is Eli the Iceman is this mnemonic device for trying to remember which one of these arrows peaks. Now, again, what we're really seeing here hopefully I don't screw this up because it's a complicated graph. We can measure voltage as a function of time, right? And so let's use this as our picture to help us understand it. Hopefully this is showing up here. Oops. Make sure it's still on there. Oops. There we go. So we're just taking one snapshot in time, right? And so at this point, right, okay, we see this is supposed to represent the voltage across the resistor. And again, the voltage across a resistor as a function of time is this curve, but its amplitude is VR, right? So maybe I'll mark it here, VR. Right? And now what we see here is the curve that would peak before that would be the inductor. So we'd expect the voltage across the inductor to peak before. Actually, it would look like this. It wouldn't be at the same, it would be like this. Sorry about that. And so right as this one's crossing the axis, the inductive is 90 degrees ahead of it. I'm sorry if my curves don't look good. All right, so I'm trying to draw this thing where we see the voltage across the inductor is peaking before the voltage across the resistor. And now similarly, we could do the same thing here with the capacitance. It's lagging. So right when the resistor peaks, the capacitor is crossing zero. And then maybe the voltage across the capacitor is bigger in this case. All right, so that's right here. And that means the next one must be about here. All right, this isn't perfect. Etc. like that. So we see there's a voltage across the capacitor here. And what we know is at any point in time, these three curves are supposed to add up to the voltage of the source. All right, so we know that this voltage must balance the sum of these three at any point in time. That's what KVL tells us. Well, it gets so messy. We see the current is no longer exactly the same thing. It's no longer exactly in phase with the source voltage. Otherwise, these curves don't make sense. So what I would like to do is go back to my simulation. That's what we're trying to understand here. Sorry, I'm trying not to misspeak. That's why I'm being very careful. Right, when I go back to this simulation here, let me get my big marker. Here is the source voltage, right? We see these different curves are peaking at different times, which is analogous to these arrows rotating around. Now here is the current. And I want you to kind of watch this for a second. And maybe what I'll do, and right now, look at this circuit. We see that the capacitor is dominant. So in case you're wondering, if you plug in all the values in this circuit, we know the inductance, capacitance, resistance, we know the source voltage, amplitude, right? From all that information, it turns out the capacitor is dominating the circuit right now. And look at the voltage across this capacitor. We see it, it's the largest voltage. So what I want to do is clear my drawings for a second. I'm going to make this a little bit bigger. Oops, I need to make it a little smaller here. And then what I'm going to do is I'm just going to do a screenshot here. Let's just do okay, let's go to paint. Oh my gosh, I didn't fire this up in advance. I'm sorry, I'm slow right now because all right, let's just go to here. Come on. This is kind of a strange way to do this. I apologize. All right. So what we can do now is I can just zoom in on this and I hit the pause button here. So this is I know I could have done this a smarter way. I apologize. All right. Whatever. This is working. So let's get this over with. All right. So in this case, we can see what's going on in the circuit for 1 split second in time. All right. And I want to point out the following pieces of information. Okay. Notice that the voltage across the resistor matches the current in the circuit as we expect. I know that the current and the resistor are always in phase. However, those are not in phase with the source voltage. Look at this. This one's still going towards its negative maximum. This one is already past its negative maximum. We see that the source voltage and the current are not in phase anymore. In particular, we see the capacitor, which is dominating the circuit, is close to in phase, right? The capacitor is not exactly in phase, but pretty much almost exactly in phase with the power supply. The capacitor is dominating the circuit and controlling the phase of the current. The resistor helps us understand the mathematical value of the current, but how much the current is shifted, the phase angle, is related to all these factors. All right, and then finally, the inductance. All right, the inductance has a much smaller voltage. Look at these values. Okay, we see the inductance is not having a huge effect. And look at the phase angle or the relative, let me rephrase. We notice that the inductance is on its way to its positive curve. All right. So this, and if you look at these arrows, this is exactly the stuff I was showing you on the board. What is the point of all this? Well, the angle right here actually relates to these arrows. And we could use this angle to figure out how much the current is shifted. All right. So what we want to do is get an understanding of how these arrows relate to how much the current gets shifted in time. So what I'm going to do is try and show this right here. And let's go back to the, let's stop the share and go back to the board. All right. So what we could do is we could take a snapshot at some random point in time here, like this. Okay. At some random point in time, I could get this source voltage out of here, right? And just consider these three arrows. And what we see is, if I want to consider how these two voltages cancel, I see that the voltage across the capacitor and the inductor are always opposite each other. And so we could see the actual voltage here. If I think about this as a triangle, maybe I'll get rid of these entirely now so I could just draw this. At some random point, we see the voltage across the resistor like this. And then we saw this voltage across the capacitor here, and it was large. And then the voltage across the inductor was a little bit smaller like this. The idea is we could change the voltage across the capacitor and voltage across the inductor into one combined term. And it's only this big, where this is the voltage across the inductor minus the voltage across the capacitor. I forget what it was now. Well, let's just stick an absolute value on there so we don't have to worry about it. But the idea here is, if I take the difference between the inductor and the capacitor, right, and then slap an absolute value on it, that's not very right angle here. There, now it looks like a right angle. The idea is there's some voltage associated with this and some voltage associated with that. Well, you could make this into a right triangle, and that's what this is trying to do here. Oops. As we go around the circle, there's some voltage. I'm just going to rotate it all the way around like this. In general, we tend to draw it like this. The idea here is the following. The hypotenuse of this is actually the voltage from the source. And then in this case, I guess we could call that V0 because we're looking at amplitudes, right? So this would be the resistor voltage amplitude. This would be the difference of inductance minus capacitance voltage amplitudes. And this would be the source voltage amplitude. These triangles, if you look at that picture, will always hold true as it's rotating, right? And so what does this mean? Well, this is the current, right? The voltage across the resistor, if I label it on this axis so you can see it better, the voltage across the resistor is equal to the current as a function of time times R. Well, I just misspoke. The voltage amplitude across the resistor is equal to the current amplitude times its resistance. The voltage across the resistor as a function of time is equal to the current as a function of time times the resistance. So, moral of the story here, these arrows give us a relationship, a triangle that helps us figure out an angle. That angle helps us understand effectively what fraction of a circle, right? So if this was 60 degrees, that'd be 1/6 of a cycle. You could relate that to 1/6 of a period. That would relate to how much shifting is going on in these curves. Whoa. All right. So in this case, we're trying to, the equations that we're going to use turn out to be on page, oh my gosh. Let me do a different screen share. We're going to here. All right, we're finally ready to start cranking out some math on these now that we've seen these conceptual things. On page 199 in my book, we talked about all this stuff last time. We talked about what happens if you have the leading and lagging, etc. All right. In this case, I want to talk about the series LRC circuit. V naught is going to be our source amplitude. I max is going to be the peak current or current amplitude. So maybe I should write that. This is an amplitude. This is an amplitude. All right. The impedance. This is like how many ohms the circuit has. This is what we were just talking about. More on that in a minute. This is the phase angle. It has to do with the shift between the current and the voltage at an arbitrary frequency. Now, a capacitor is not a resistor, but we can convert capacitance into ohms using this equation. We can convert inductance into ohms using this equation. All right. Now, be careful. There's a watch out here. F is the frequency of the function generator or the source frequency. It is not going to be resonance frequency. More on that in a minute. Now, this term, okay, so that's that. Let me clear my drawings and scoot down. Oops. If we want to understand the functions of time, we're going to look at these types of things right here. So the source voltage as a function of time, let me get my annotation here. Remember, this is V naught. Remember, the current amplitude is the voltage across the resistor amplitude divided by R. And so I'm just going to write amplitude here just to make that clear. If you take the amplitude and divide it by R, we get this I max. Then we got to multiply by sine omega t, and phi, the phase angle that tells us how much the curve is shifted, is related by this triangle that we've been discussing. Okay. If I want the voltage across the capacitor or the inductor, we can see those are shifted by 90 degrees from the resistor. Well, so one of them shifted pi over 2 and one of them shifted negative pi over 2. Again, there's a phase angle in there, and then there's also the shift associated with the leading, the Eli the Iceman leading and lagging type stuff, this lead and lag. All right. If you want to get the peak voltage across the capacitor, we get the amplitude. Remember, Imax is amplitude times XC, the equivalent of these ohms. All right, there's so much here. You're probably feeling lost. We need to work through an example. That time, we just got to do an example here. So I want you to keep this page open, and I'm going to try and walk you through all this. All right, so this is, again, page 200. So have this handy. And let's go to a numerical example so we can make sense of this. Whew. This is tough stuff. Whoops, I don't want that. I want this one. All right. I want to have a circuit that looks like this. I want to have an AC source, 10 Henrys. I want to have, oh, maybe I should show you what circuit I'm doing here. I made a simulation of this just so you could see it. Here's that circuit. Let's get rid of this for a second. The idea here is I've got a 10 Henry inductor. I've got 4 capacitors in series, so that's why I wrote C over 4 on the whiteboard. And then I've got a 10 ohm resistor. I've got a 10 volt source here. Notice there's a 10 volt source, so V naught is 10 volts, and you can change the frequency to whatever I want here. So I could sweep the frequency and choose whatever frequency I want. All right. And then what we can do is we're trying to understand the current versus the voltage, right? And if I could show these both, maybe what I could do is, oops, let's slow this down a little bit. Let it reach equilibrium, steady state here. All right. So what we're trying to do is understand this at some point in time, and we see that the current and the voltage are not peaking at the same time. Let's do the math and understand how they're differing. Okay. That's what we're trying to figure out here. Here's the circuit. So I took those 4 capacitors in series. They were 0.05 each, and I divided them and got these numbers. All right. So our source voltage in this particular problem was 10.0. And the frequency I think I ended up using was, let's say I use 0.6 hertz. All right. If I need omega, I can just multiply this frequency by 2 pi. So I'm going to do that. 2 times pi times 0.6. 3.67 or 3.77 radians per second. To be clear, these are the source parameters, right? So, and actually, let's just get these. That's the source frequency. All right. The resonant frequency is different. This is the frequency which I choose to run my function generator. This is the frequency I choose to set on the dial. This is the special frequency that would give me maximum amount of light. Okay, so in this case, this is calculated using a formula, 1 over the square root of LC. So if I punch in these numbers for that, I found that it's actually, and again, I'm just punching in these numbers into this formula, and I wrote it down. I got 2.83. This is an omega. It should have units of radians per second. This corresponds to a frequency, this is an angular frequency. If we want to get this in units of hertz, right, this corresponds to 0.4, oh, how about I write it like this? It's omega naught divided by 2 pi, which in this case is 0.45 hertz. Look at this circuit. We are operating at a frequency slightly above resonance. Well, if we're operating at a frequency above resonance, who should dominate? for this particular circuit, the inductor will dominate, right? Inductors are the ones that shut down the circuit at high frequency. Capacitors shut down the circuit at low frequency. So in this case, our inductor is going to dominate. So I'm going to write that. Inductively dominated because operating frequency F is larger than resonant frequency F naught. Or said another way, F is greater than F naught. Because we're operating at a frequency above resonance, the inductor will dominate this circuit. Great. All right. Now, what we could do is we could figure out the capacitive reactance. That is equal to omega L. It is not omega naught L. It is not the resonant frequency times L. It's the operating frequency times L. And we could also figure out the capacitive reactance 1 over omega C. All right. So these are the reactances. Okay. This is the inductive reactance. And this is basically how we convert inductance to ohms for an AC circuit. So punching in my numbers here, well, this is actually not too bad. It's just 10 times this. So it should be 37.7 ohms. All right. XC, that's the capacitive reactance. I'm going to grab my calculator here. So omega is 3.77. The capacitance was 0.0125. And now I'm going to flip it. So I get 21.2 ohms. So in this particular example, we see there's more ohms associated with the inductance. That's what I mean when I say inductively dominated. The inductor produces more ohms than the capacitor does. Okay. Now in this case, we could keep going. We could get what's called impedance. All right, and so to be clear, these are called reactants. I could get impedance. Total impedance. So that symbol is Z. It's in ohms. And this is the effective amount that the circuit impedes current flow or resists current flow. So if we add all three of these together, for now, I'm just going to tell you the formula. It's the square root of R squared plus XL minus XC quantity squared. All right? This relates to that triangle we were looking at. I don't know if you want to remember this. Z is like the total impedance of the circuit. On this axis, we have the resistance. And here, there was that difference between the capacitor and the inductance. And it turns out the standard way of writing it is always to write XL minus XC. So I apologize if I did that backwards with the arrows a few minutes ago. All right. And then we can use this to figure out the phase angle. Well, let's get a value for this particular Z. In this case, R squared was 10. So we're going to get 10 squared plus XL minus XC. In this case, XL minus XC. Let me see what that is. Oh, whoops. I could just say 37.7 minus 21.2. That's 16.5. And we got to remember to square root it. So that x squared plus 100 Then we'll square root that. I get 19.3 ohms. I don't care about sig figs right now. This is the total amount of ohms associated with this circuit. So what we've seen is if you can figure out the frequency that you're operating at, you can use these reactances to figure out the equivalent number of ohms. Now, because there's this whole leading and lagging issue, which was so complicated, we have to consider the fact, well, I don't want to go into it. We got to do it this way. All right, enough for right now. Okay, furthermore, we can get this phase angle. Now, when you look at this triangle, it's screaming right out at you. You could do inverse tangent, right? We know XL minus XC and R, so I'm going to do tan inverse of XL minus XC, a quantity that we know, over the resistance. In this case, the numerator is 16.5. Ohms divided by 10 ohms. So we can get the angle. So 16.5 divided by, well, that's just tan inverse of what? 1.65. So I got an angle of positive 58.8 degrees. Positive. Okay. So what can we, all right, so this is the basic math of this thing. What we've done so far is figured out the total number of ohms in the circuit and the phase angle. This phase angle is going to help us understand how much the current is shifted. All right, so now I'm going to go over to the next board. Let's do this. All right, give me a sec. It's interesting trying to record this without students to talk to. I feel like having you to talk to makes me a little bit better because I can tell what's not working when I'm speaking. Here it's like I've got nothing to judge when I make a confusing statement. But maybe all my statements are confusing, huh? All right, this is a tough section. All right. So now what I want to do is get some of the information from here that we had before, but I'm just going to summarize it. All right. So we had F was equal to 0.6 hertz. We had omega was 3.77 radians per second. That's our operating. Freak. We know omega naught and F, let's write them in the same order. We were able to figure out the resonant frequency was right. And maybe for you guys, I might as well zoom in. Just summarizing all the things we know here. We found Z, the total impedance was 19.3 ohms. And we found that by using XL was 37.7 ohms. XC, the capacitive reactance was 21.2 ohms. And the resistance was 10 ohms. Furthermore, we found out doing some math that the phase angle was positive 58.8 degrees. Now you might be saying, why are we using degrees for this and radians for that? Well, this is the standard way. All right, so we're going to keep doing it the standard way. What does this mean and how can we get to this plot? What I want to understand next is the plot that we've been trying to understand, which is voltage as a function of time. All right, so, well, our source voltage as a function of time right? That's V naught, which did I label that somewhere? What was V naught? I think, oh yeah. V naught was equal to 10.0 volts. That's the amplitude, right? So this thing's going to oscillate up and down at 10 to negative 10. All right. Sine of omega, which was 3.77 radians per second times time. All right. So again, this is not omega naught. This is the operating frequency, the frequency of the dial I chose. The resonance frequency tells us something about whether or not this circuit was inductively dominated, right? We said because F is greater than F naught, inductively dominated, or the inductor dominates. Another way of saying that is, instead of saying ice, we should say Eli, okay? If the inductor is dominating, I'm going to write down Eli. Okay, what does that mean? This means voltage leads current. Okay, voltage should peak first. So now I know the current needs to be shifted. How much? Well, we found the phase angle was 58.8 degrees. So that means it's about, well, this is about 60 degrees. So that's about 1/6 of a cycle, or 60 degrees is, I guess, 1/3 of 180. Well, let's just try and eyeball it here. So we know that this is when that's peaking. This is 90 degrees, right? So maybe the current's peaking right about here, right? And then here it's reaching its peak there. So the current's going to peak a little bit afterwards, right about there. Going to hit 0 a little bit afterwards. Going to hit 0 a little bit afterwards. So this is my attempt to draw that. Whoops. All right. And the idea here is this is a certain amount of time, right? There's a time shift. I'll call that delta t. Well, we could do a quick ratio to figure this out. If you wanted to know, you could take the delta t over the period. That should equal 58.8 degrees out of 360 degrees. The idea is if you wanted to find out how much time these are shifted, we could use this thing called a phase angle. And so we see that delta t, the time shift between the two peaks, is the period times 58.8 degrees out of a full 360. Now keep in mind, you might be saying, well, geez, what's the period? Well, we know that the period, we know that omega is equal to 2 pi over the period. If you know the operating frequency and you know 2 pi, we can flip this around. We see that the period is 2 pi over omega. So if you plug in the number for omega, you could get this time shift. And that's what we were trying to figure out. This is a numerical way to quantify it. What do the equations look like for current? All of this can be summarized here. The current as a function of time is given by I maximum times sine of omega t. Well, I can't just have omega t here. I have to shift it to the right by this phase angle. Now, this is where it gets super annoying. All right. I want to talk about, this is where it's annoying. That's funny. All right. Remember, this is radians per second, and this is degrees, right? Generally speaking, when people write these problems out, they use radians per second here. They write degrees for the phase angle, but you have to remember to convert if you're going to use it, you have to convert to radians. Phase angles are standard in degrees. That's how people usually express them. But then if you want to plug it in, we're going to have to convert it to radians. So always watch your degrees and radians in this part of the class. Watch out for this term. This is not the current. This is the current amplitude, right? It's the maximum amount of current that flows, right? So to be clear, this is I max, so to speak. Now, here we run into trouble, right? Voltage and current have different units. So it doesn't make sense. I actually have to multiply by R, the resistance. Remember, current times resistance, current amplitude times resistance gives you the voltage amplitude across the resistor. So if we needed that information, now that we know that, oh, did I ever write down the current amplitude? I don't think I did. Okay. If you want to get the current amplitude, there's another equation we saw somewhere, I don't know where. It's equal to the source amplitude. These are all amplitudes. Divided by the total impedance. So in this case, and maybe I'll write this up here. Let's get that current amplitude doing some math. All right, so the current amplitude is 10 divided by what number did we have here? 19.3. All right, so I get 0.518 amps. I'm going to round. Make sure that still shows up. Just running out of space. Okay, so we've got 0.52 amps is the current amplitude. So what we could do now is we could use this current amplitude to figure out the voltage amplitude across the resistor. The voltage amplitude across the resistor as an amplitude is I max R. Well, in this case, the resistance was 10, which makes this a little bit easy. It's just 5.2 volts. So going back to our plot, right, now that we know the current amplitude using this equation, which was given on page 200 or something, we could get this voltage. And so that gives us a reference level. Instead of having to write I max times R, we could see that this is peaking at 5.2, figure not to scale, right? And this is negative 5.2 volts. So the voltage here is in volts. All right, so now we understand the voltage versus time and the current versus time, okay? To be clear, this is essentially voltage across the resistor as a function of time, which relates to the current as a function of time, right? So far, so good. Whew. Now, this was all done at one particular frequency, right? We just did this, all this work for one particular frequency, right? So if you operate this source at 10 volts at this frequency, we get that phase angle, etc. Now what we could do is we could actually change the frequency. If we change the frequency, some of this stuff changes and some of it doesn't. Okay, the inductance, capacitance, and resistance will not change. The source voltage amplitude will not change if I just change the frequency, right? The resonant frequencies will not change because those depend only on inductance and capacitance. What will change are the reactances in ohms, because these depend on operating frequency. So we need to look carefully at anything on our board that is affected by the operating frequency. The resonance frequency is a fixed number. The source voltage amplitude is a fixed number. If you change these, the reactances change. If you change these, right? Well, if you change the frequency, this may change. We may no longer be inductively dominated, right? Because maybe the capacitance, the capacitive reactance gets larger. The total impedance might change. The phase angle might change. The way this graph looks might change, etc. The numbers associated with it, both the vertical scales and the horizontal scales and the angle and the time between them might all change. Right? All right, so where do I want to go with this? Let's take a second and look. There's one last piece I got to tell you here somewhere, and I got to do this. So let's go back to our simulation and get you out of this section. All right, so let's run this simulation again. All right, we've got some lag here. Oh, I've got too much running here. All right, let me see here. Well, I don't know why that's going so laggy here. Oh. All right, let's go back to this one. Maybe it's this one that's causing it to lag. All right, and so now we could do this piece here. And let me make this just a little bit smaller here. All right, so now I can actually see what's on there. All right, so what I want to do now is I want to change the frequency and see what's going on. All right, so again, I don't know if you can see where I'm messing around here. I'm changing the frequency. I'm keeping the source voltage amplitude, the resistance, the capacitance, and the inductance all the same. It's only this that I will be changing. All right. And now in this case, it's not exactly the same numbers as before, but we're trying to understand this middle plot now. Okay. We've understood pretty much all of this stuff. We figured out the phase angle and the total impedance. We've learned all that. We could talk about whether something's dominant or not. We talked about where this is peaking relative to this. We've talked about this already. So now, again, we want to focus our attention on what this means. Look what's going to happen. As I change the frequency, I'm going to change the amount of current flow. Now, wait a minute. What is this z to the minus 1? Well, remember that current amplitude, I max, was equal to V naught over Z. So Z to the minus 1 essentially is telling us something about not current, it's telling us about current amplitude. Okay, so a plot of Z to the negative 1 says, where will I get the most light bulb brightness? Okay, so let's do this. As I go to a very low frequency, right? At low frequencies, capacitors get filled up. At low frequencies, the capacitor dominates. The capacitor dominates. It's essentially reaching full charge and blocking all current flow. There's almost no current flow. Okay? If I go to high frequencies, oops. If I go to really high frequencies, the inductor is dominating. Okay? When the inductor dominates, there's still no current. All right? I should mention this. Look at the phase angles. When the inductor dominates, you get a positive phase angle. Whoops. Right? When the capacitor dominates, we're going to get a negative phase angle. All right? So this 86.7, when you plug into these equations over here, you actually get a negative phase angle. More on that in a minute. Now watch what happens as I sweep the voltage. Or sorry, sweep the frequency. We're starting to get more and more current. Look at the phase angle. It's getting close to 0. Right at this point, when XL equals XC, the green arrow and the blue arrow are exactly balanced in size. Because they are out of phase with each other, they exactly cancel out. When you run the circuit at resonance, the inductor and the capacitor balance out and they have no effect on the circuit at all. Crazy. Look at how big that current flow is, right? At resonance, this voltage balances that voltage. Notice the polarity of those voltage. They are the same in size, but the polarity is opposite due to the leading and lagging business. At this value, we get maximum current amplitude. That wave is as big as possible. We get maximum current amplitude. So I max, that's the maximum value for I max. All right. Now we understand everything in that. Well, I don't know if you understand it, but now you're ready to actually practice this stuff. So the idea there, if I could go and find somewhere to squeeze this in. I'm going to zoom out just a little bit. Sorry. I'm going to move over just a little bit. So I'm going to draw this last one right here. Okay. What we just saw is current. Oh, maybe I'll draw it in red. The current amplitude changes as a function of omega or frequency, however you want to do it. Now to keep in mind, I max was the symbol we were using for current amplitude, right? At low frequencies, the capacitor locks everything down and doesn't allow current flow, right? So this is capacitive dominated. Over here, the inductor dominates. At high frequencies, you're changing so quickly, the change in flux is opposed by that inductor, and it locks down the current. At some special frequency, omega naught, we see that XL happens to equal XC. The capacitive reactance, the capacitive reactance and the inductive reactance balance. We discover when that happens, if you plug in these two equations, right, you see omega L equals 1 over omega C. This is the special frequency. It gets labeled omega naught. When you solve for that, I don't know if you see this, you're going to get 1 over the square root of LC. That's where that equation comes from. So right at this value, we get the most possible current amplitude, like that. And at this special case, only at this special scenario, only when we're operating. So I guess what I'm saying here is this is the only time when omega equals omega naught. If you're operating at the special resonance frequency, you get the most current possible. All right. We're probably going to need to do several more worked examples, but hopefully this is maybe making a little bit of sense. Why, if you recall when we started this, what were we talking about? This is the plot we were trying to understand when we looked right over here at this thing. The idea here we saw this light gets bright at one special frequency. And we were trying to understand what that frequency was. What did we just do? We did all the math to understand what frequency should be the brightest. And by the way, I happened to check this out. It seemed to match with the capacitance we used, which was 11 nanofarads, and the inductance, which was 11 millihenries. We get a value of about there, 14 kilohertz, which if I've got actually, what do I have there? About 14.5 kilohertz for this example. And then when we plug in the numbers for these, if I use 11, I get approximately 14.4 kilohertz. Yeah, so this seems to match up to what we expect. All right. All right. And I'll just zoom in on that demonstration one last time here, just so you could see. Again, numbers that we're using right here. 11.14 nanofarads, and the inductance was 10.9 millihenries. So if you want to get exactly, and so again, I found 14.4 kilohertz, and I'm operating at 14.5, and it seems to be the brightest. Okay, enough for this section of the lecture. Holy cow.